I don't know about you, but I have always loved David Attenborough documentaries, especially ones about wildlife, and those ones in particular I adore are just places like Africa. You probably know the ones I'm talking about, where you see those incredible scenes of things like wildebeest wading their way through crocodile-infested waters, just trying to get to the other side of a river, or the incredible menagerie of animals that will come down to drying waterholes to drink, the zebra, the antelopes, and everything else. And then there's the plains of places like the Serengeti, absolutely majestic places, incredibly diverse, where you see the big seasonal migration of animals year after year after year. But have you ever asked yourself, why don't we have something like that here in Australia? Now, to me, one of the interesting things about the Australian continent is that it is an island continent, firstly. So Australia's wildlife have been evolving in isolation for literally millions and millions of years. And because of that, we have some really unique animals down under. So things like our wombats, koalas, platypus, emus, these animals are known from nowhere else on the planet itself. And this might be the normal view that people have when they think about the wildlife of places like Australia. Now, to me though, as a paleontologist, I look at this and it's anything but normal. And the more I think about it these days, it feels really super weird. So when I have a look across the landscape, to me it's not normal that the biggest native herbivore that we have is something like a kangaroo. And it's not normal either that the biggest native predators that we have are things like dingoes. So when you have a really deep look into things like the fossil record itself, you'll see that until very, very recently, geologically speaking at least, that these ecological roles have been held by different types of animals in the past. And so Australia, believe it or not, used to have really large animals, very similar to places like Africa and other parts of the world. And we also had the diversity in these ancient ecosystems that were comparable to places like the Serengeti itself. But we don't anymore. And it's because those animals have gone extinct. Now, I'm not here talking about dinosaurs today. I'm talking about the Ice Age megafauna of Australia. Now, when I say the phrase Ice Age, I'm specifically talking about a portion of geological time known as the Quaternary. So the Quaternary started around about 2.6 million years ago and extends all the way through time until this very second right now. So we're still in the Quaternary. So the onset of the Quaternary was marked by these really incredible shifts in global climates. Now, as we started to move through time, we would see temperatures fluctuate incredibly. We would go through periods that are nice and warm, to periods that are nice and cool, and continue that kind of motion. Now, it was during those cooler phases where temperatures would drop as much as 8 degrees Celsius below current levels that the Quaternary earned the right to call itself the Ice Ages themselves. So it was during those cool phases where we would see incredible glaciation events on the continent. So these huge ice sheets would form in some parts of the world. In North America, for example, these sheets are estimated to have been up to about 3,000 metres in thickness. In Australia, we didn't have glaciers so much, but we did see significant shifts towards things like aridity, and we would have these incredible mega droughts that could last for thousands of years at a time. Now, it was during this period of change that we also saw massive sea level fluctuations as well. So at times, sea levels would drop by up to 130 metres below current levels. So when that happened, it would be possible to walk from places like New Guinea all the way down into mainland Australia and even down to Tasmania if you really wanted to. Now, it was underneath this backdrop that despite these incredible changes, this little corner of the world still remained isolated to the rest of the planet itself. So the Quaternary saw some really incredible things happening as well, like the first members of our own species, Homo sapiens, emerged up out of the grasslands of places like Africa and eventually began their incredible migration across the planet. So they arrived in places like Southeast Asia around about 75-ish thousand years ago, and then basically island hopped their way down into Australia, arriving about 10,000 years after that. Now, when the first people set foot in Australia, they would have been encountering a type of wildlife that they had never seen at all as part of that global migration journey. So things like our wombats again, our kangaroos, our emus, our platypus, these things would have been strange enough, but then there were also the Ice Age giants. Now I want you to try to imagine this just for a second. Imagine being out on your favourite bushwalk, just immersed in the wilderness, picking out the scents and the sights of nature itself. Imagine you're walking along and suddenly you hear a rustling behind you, and you turn around and you see a kangaroo. But you're used to kangaroos being this big, but this kangaroo was literally that tall right there. Out in the distance, you see a wombat lumbering past, and this wombat is the size of a cow, believe it or not. You know, next up, you hear another noise coming past you, and this is a giant flightless bird 350 kilograms worth of just meat and beak, believe it or not. So way bigger than any emu that you've encountered before. Now, in these Ice Age environments, the top land predators were things like these marsupials that looked and behaved a little bit more like African lions, so they're pretty weird. There were land-dwelling crocodiles, and there were enormous venomous goannas at the same time. Now, the biggest members of the Ice Age megafauna of Australia was this group called the diprotodontoids. And that's a real mouthful, I know, but these were basically, again, strange herbivorous marsupials that were sort of wombat-like, but they walked around with elephant-like legs. Now, the biggest member of this group was this thing called Diprotodon, and Diprotodon is world famous because it's the biggest marsupial that ever existed. So it stood around about my height at the shoulder, got up to about 3,000 kilograms or so in body weight. So that's the combined mass of about 40 individual people. So all up, back in the Ice Age, we had around about 90 different species of megafauna doing their things. But we don't have them anymore. Why not? They've gone extinct. So there's been two dominant ideas that have been put forward that might explain the extinctions, and they come down to this. The idea that climate change or humans may have wiped these things out. So the climate change argument suggests that these long-term shifts towards more arid climates as we go through time, coupled with those mega droughts, was enough to wipe out the megafauna. Others have suggested that maybe it was humans coming in and inadvertently overhunting the megafauna to extinction, or maybe they've changed landscapes in a detrimental way through things like burning of the bushland itself. So what does the data say? Who or what wiped out the megafauna? And the answer to that is this. It depends who you talk to. Now, there's some researchers that are out there that are so bold and courageous and say that they know everything, and they'll proudly claim that it was things like climate change. They'll know exactly that that's what happened. Other researchers will scream from the rooftops and say it wasn't climate, it was humans. So to illustrate this point, I want to share with you just some titles of some scientific papers that have been published in the last decade or thereabouts. So you'll get a bit of a sense for the lack of consensus in this debate itself. Now, the thing that really blows my mind, if you have an opportunity to read these papers, some of these findings are based on exactly, or at least in part, the same sort of data sets, so it's shared across these different papers. So depending on the way that you look at your analyses, the assumptions that you make, the data that you choose to include or exclude, you can come up with any variety of answers, right? But the big takeaway for me when I see something like that is that we just don't have enough information still. So when we think about the fossils themselves, you know, they look fantastic in those reconstructions, but most of these species are represented only by fragmentary remains, so scrappy bits of fossils here and there. So because of that, it's really, really difficult to reconstruct what these animals were like in nature itself. And the other problem here too is that we just don't have enough fossils that have been dated. So for some species, we don't even know when they went extinct. It's a real challenging thing. So we need more fossils, we need more field work, and obviously funding. We need more dating, and we need more of those kind of studies that can bring those fossils kind of to life so we know what they were like in the Ice Age ecosystems. So in many ways, what we're kind of trying to do here is put together a puzzle, but the problem is that we don't have the box anymore, so we don't know what the picture should really look like, and we're still missing too many of the puzzle pieces. But it's really fundamental that we find out the truth of this stuff, because it's not like we're talking about an extinction event that happened millions and millions of years ago, like what happened to the dinosaurs. We're talking about an extinction event in the same geological period in which we currently live. And this is a geological period that tells a story of all of us. Now, I'm really happy to say that there have been some wonderful new papers that have come out in the last few years alone. They're really starting to change our understanding of these Ice Age environments. So we've got a whole bunch of new species that have been described, you know, completely unknown previously in science. So there's multiple species of crocodiles, including this enormous freshwater crocodile that was weighed up to about 1,000 kilograms, but it stalked the waterways of inland Australia. We now have evidence that we used to have vultures in Australia, and we certainly don't have vultures at all anymore. So these would have been things like the garbage collectors of the Ice Age, just scavenging on the carcasses. We also have seen some reinterpretations of things like the paleobiology of kangaroos, and we've been able to bust the myth now that all kangaroos hop. So one group of researchers have looked at some of the biggest kangaroos, and they've determined that these things were actually bipedal. They were too big to get off the ground. So they walked around exactly like you and I, just on two legs, believe it or not. Now there's another group of kangaroos as well that are now interpreted to have been quadrupedal, which means that they walked around on all fours, which is really quite remarkable. Speaking of new research, though, I want to introduce you to my friend, Frank. Now, Frank is a diprotodon. I brought him with me today. So diprotodons were that big marsupial I was talking about before. So we found Frank a few years ago when we were going for a walk up on the Darling Downs, which is around about a 2-hour drive west of Brisbane. And we love to go up to the Darling Downs and have a walk down the creeks, especially after big rain events. So we hope that the floods will reveal new fossils. And that's exactly how we found Frank. So what Frank represents here is the front part of the lower jaw of a diprotodon. You can see the bony chin through that area, and we've got the 2 broken front teeth, unfortunately broken in that cross-section right there. But this is a really great example for where the name diprotodon actually comes from, because if you break that down, diprotodon literally translates as 2 front teeth. And you can see those 2 teeth in the specimen here. Now, you might be thinking like, yeah, Frank might not be the prettiest fossil that you've ever seen. And I'll be the first person to admit that that's true. But there's a little bit more to Frank than meets the eye. And we were lucky enough to find the back end of Frank's lower jaw that you can see right here. So when we pulled this out of the ground, we all stood around and we're just absolutely blown away with how majestic Frank must have been in life. So we found out a few things about Frank as well. So Frank was a boy, and he's a very, very big boy, actually. He was about as big as what a diprotodon would actually come. We know that Frank had an interesting life. He did pretty well up until adulthood, but he didn't have a very long life after that. And when we look at the fossil deposit where Frank has come from, we've been able to figure out that Frank probably died in a drought, unfortunately. Now, when we've dated Frank and other fossils of diprotodons from Eastern Australia more broadly, we've been able to determine that diprotodons thrived for hundreds of thousands of years locally, all the way up until around about 30 or 40,000 years ago when they drop out of the fossil record. Now, that period is a long time after the first people came into Australia, but it's a period that coincides with some really intense climatic changes. Now, our investigations into diprotodon have gone quite a bit further away from Frank as well. And one thing that we've been able to do is take other diprotodon specimens from Frank's original neighbourhood, and we've been able to determine that diprotodons are what we call seasonal migrants. So they would be, over the course of a 12-month period, travelling hundreds of kilometres around in a given area, chasing its preferred food source. So it would go somewhere, and by the end of that year, it would be back to where it started. So exactly the same kind of ecological thing that we see in terms of the Serengeti animals these days, the beautiful migration. So you might be wondering, though, how is it possible to tell if an animal that is known only from fossils, would undertake that kind of migration? Well, it's kind of a little bit like this. As my partner loves to remind me all the time, every time she sees me eating a bar of chocolate or chips or drinking beer, she says to me, "You are what you eat." And that's actually true, because the chemical signature of the foods that you put into your body becomes fixed into your tissues. But it's also true that you are where you ate, especially if you're a herbivore. So imagine that we've got some plants that are growing on a particular soil type. The chemistry from the soil becomes fixed into the growing tissues of that particular plant via its roots. So if you're a herbivore that comes along and you eat that plant, that chemical signature from the soil becomes transferred into your tissues. So if you've got an animal that is migrating or moving across the landscape, going across different types of soils, and eating those plants, you would expect to find those different soil chemical signals in your own tissues. And in this case, what we're talking about are the fossils. And that's exactly what we found with diprotodon. So diprotodon was a seasonal migrant. And in many ways to us, it's kind of like the original grey nomad of Eastern Australia. So grey nomads today love to travel north and south, and diprotodon was doing exactly the same things, but hundreds of thousands of years before the current grey nomads, of course. But when we first found this, we were absolutely blown away, and we couldn't stop thinking about how similar the Ice Age ecosystems of Australia must be to places like the Serengeti these days. They're just so much more ecologically complex in the past, and we have to just really try to reimagine what we think we know on the basis of this new evidence. Now, when we compare that to ecosystems of today, we don't have things like seasonal migration operating at any kind of level at all. So this is a type of ecological phenomenon that's completely extinct. But we want to know why. Like, why don't we have these mass mobs of migrating megafauna anymore? What is the ecological consequences of their extinction? What is the fallout for that? And how does that affect the ecosystems that we still have around us today. The more I look into this work, the more I draw an analogy between the fossil record as being like an ancient crystal ball, because when you can look into it really, really deeply, you can see how past ecosystems have navigated the challenges of things like climate change. So whether that's things like fluctuating carbon dioxide levels in the atmosphere, global warming, it could be those sea level changes I was talking about before. And a lot of the times when you look into the fossil record, you can see these things happening underneath the shadow of human influence. Now, while we can't rewrite the history of Frank and any of the other megafauna, we can start to weave their stories into our own futures. So by better understanding the tapestry of the existence of these incredible megafauna, there are lessons to be learned there that are going to be absolutely fundamental to better allow us to monitor, maintain, and nurture modern ecosystems. So if you think about animals that we still have today, so you've got your koalas, your kangaroos, your Tassie devils, your emus, your platypus, echidnas, whatever. These animals didn't just magically appear in Australia recently. These animals lived alongside the megafauna for hundreds of thousands of years, and that's also true of any native animal or plant that you can think about these days. But how did they survive the challenges of the ice ages themselves? Why didn't they go extinct? Now, if you can understand how those organisms that we still have today responded to those same challenges of the megafauna, that's going to be some really important information that will help allow us to make predictions of how future climate change may affect ecosystems that we have today. So it really feeds in massively to the whole conservation type of questions that we have today and challenges. So it's not just about looking back, though. It's about realising that the echoes of the past really reverberate with the challenges that we've got going forward. So next time that you ever see a fossil of a diprotodon or one of these massive kangaroos on display in a museum or illustrated in a book or reported on the news, I don't want you to look at it and think, wow, but think how instead and why. So these animals have left a really astonishing legacy. And let's just not look at them merely as objects of fascination or curiosity, but let's allow them to inspire us to really take charge of the world around us and to come up with better ways that we can safeguard modern biodiversity itself and to help forge a sustainable path for the generations that are to come.